Welcome to the Explainer. Today we're launching into a truly fascinating Grade 7 robotics investigation, and we're basically going to crack a case about how robots actually think. So put on your detective hats because we're going to be looking at some hard scientific evidence today to figure out what's really going on inside a robot's brain. If you've ever built a robot and wondered why it does exactly what it does, or maybe why it sometimes does exactly what you really don't want it to do, well, you're in the exact right place to find out. Okay, let's dive right into this. When you see an incredible robot zooming around a room, perfectly avoiding obstacles and completing these incredibly complex tasks, I want you to ask yourself a crucial question. What truly controls that robot's behavior? Is it just the gears, the motors, maybe the wheels? Does a robot's physical body completely dictate what it can and cannot do? Take a second to really think about that. If you build a robot a certain way, with a specific set of treads and a very specific set of arms, is its destiny completely fixed from that exact moment on? Now, if your gut reaction was to say yes, well, you definitely aren't alone. In fact, that brings us to a massive misconception in the world of robotics. Let's call it the myth. The myth states that a robot's physical construction entirely determines its capabilities, with the code playing just a minor secondary role. People look at a machine and they often think, hey, if it has wheels, it rolls. If it has a sensor, it senses. They assume the hardware is the absolute star of the show and the software is just there to, simply flip the on switch. Well, today, we're going to scientifically test this myth and we're going to bust it wide open using some hard, undeniable evidence.
So that brings us to the official essential question for our Unit 3 investigation. How does program control flow make robot behavior more flexible? I want you to laser focus on that work right there. Flexible. Flexibility is the key difference between a dumb machine that just does one boring thing over and over until it finally breaks, and a smart robot that intelligently adapts to its environment. Over the course of this explainer, we're going to see exactly how we unlock that crucial flexibility.
So, what exactly is this secret weapon? By definition, program flow is the order in which a robot executes code. It uses sequences, loops, conditionals, and functions to make active, real-time decisions. Think of it kind of like a recipe, or better yet, it's literally the robot's actual brain. The physical build, the hardware, the metal, the plastic, the wiring, all of that is just the muscle and bone. But the program flow? That's the highly structured set of instructions telling those muscles exactly when, where, and how to fire. Without program flow, the most advanced, expensive physical robot in the entire world is basically just a very heavy, very quiet paperweight. To really prove just how vital this digital brain is, we need to set up a controlled experiment. We're going to take two completely 100% physically identical robots. We're talking the exact same motors, the same wheels, the exact same chassis, and the same sensors attached in the exact same spots. Everything on the outside is completely identical. But on the inside, they are running entirely different programs. Now, why set it up this way? Because if the hardware is exactly identical, any difference we see in their behavior out there in the real world absolutely must come from the software. Now, what's really interesting is when we compare the two brains we're putting into our identical bots. Program A is a basic single-action sequence. The instruction is incredibly simple. Move forward once. That's it. It's a straight, unchanging line of code. But then we have Program B, which uses an advanced continuous flow. It's told to loop continuously, and right inside that loop, it has a conditional statement checking a sensor. It's constantly asking a question, is something in my way? Let's see how these two very different minds handle the exact same physical world. All right, put your investigator glasses on, and let's read the data we've gathered. Robot A, with our standard physical build and a simple sequence program to move forward, does exactly that. The observed behavior? It moves blindly forward and smacks right into a wall. Boom, end of story. It did exactly what it was told, but it certainly wasn't smart. Now, look at Robot B. It has the exact same standard build, the exact same physical body, but it's armed with a loop and a conditional. The observed behavior this time? It senses the wall before it hits it, beautifully turns, and seamlessly continues on its way. We've just proven that giving the exact same body a different set of instructions completely alters its physical capabilities. The hardware didn't change one bit, but the robot's ability to survive in its environment completely transformed. So how exactly does Robot B's program flow work in real time to prevent that crash? Well, it follows a continuous, rapid-fire 4-step cycle. Step 1, check the sensor for an obstacle. Step 2, evaluate the conditional statement. It's basically asking the logic gate, is the path blocked, yes or no? Step 3, act based on that specific answer. If the path is clear, move forward. If blocked, turn away.
And finally, step 4, loop back and repeat. Check, evaluate, act, repeat. Check, evaluate, act, repeat. This loop is happening incredibly fast inside the processor, literally hundreds of times a second. It's this continuous flow of logic that gives the robot its awareness.
Okay, so the crucial takeaway here is simple. Myth busted. The evidence we just walked through undeniably proves that the same physical build behaves very differently depending entirely on the program flow controlling it. The myth that hardware dictates everything is completely false. Your robot's true superpower, its adaptability, its flexibility in dealing with a messy, unpredictable world, all of that comes directly from the code you write. The program flow is the absolute true source of a robot's intelligence. And this is exactly why this matters for your own robotics projects going forward. By mastering program flow, you unlock massive potential for your builds. It allows you to organize your code efficiently so it's not some tangled, unreadable mess. It lets you predict program behavior accurately, meaning you'll know exactly what your robot will do in your head before you even plug in the battery. It gives you the power to debug complex programs when things inevitably go wrong. And most importantly, it lets you make your robot flexible to totally new situations. You become the true master of the machine. Let's wrap up our explainer today with a challenge, a transfer task to test your brand new skills as a robotics detective. Imagine you're running a robot, and suddenly it does something completely unexpected. It spins in circles, or maybe it refuses to move entirely. Here's your final question. What evidence would you gather to determine if that glitch is a hardware build issue, like a loose wire, a dead battery, or a jammed gear, or a program flow issue, like a broken loop or a backwards conditional statement? How do you actually isolate the problem? I'll leave you to ponder that debugging mystery. Thanks for joining me on this investigation of program flow, and keep building smarter bots.